Okay, I think we can get started. We are at noon. Today, we're happy to have Maria Martone from Stony Brook and Simon Center. Please take it away.
Great. Thanks, Ibu, and thanks everybody else is organizing this amazing series of seminars and for inviting me to talk. Okay, great. So the title is pretty self-explanatory of my talk. I'm going to be talking about geometric constraints on the space of 4D theories. It's assumed, as many probably of you know, that is super conformal field theories. So rather than giving a kind of a more technical talk on a specific result, I decided to give a bit of more of an overview of the many results that we obtain, in the hope that really, since there are many experts in the audience, we can maybe we can have an interesting discussion. And I'll be very frank and upfront on what I think are the open questions. And again, feel free to please, chime in and tell me that your opinion, so that really we can all learn from this. So this talk it's going to be really based on many more papers, but particularly on these 4 papers that I wrote in collaborations with Philippe Argyris and Bourget, Antoine Bourget. They come out in the last year and a half, more or less. But there's also a lot of upcoming work with Philippe Argyris, Chris Beam, Jack Distler, Carlo Menaghelli, Leonardo Rastelli, Wolfgang Pellers, and Gabriel Zaffri. I have to share with you guys that as I was typing this up this morning, I noticed that all my collaborators are men, and that kind of generated a little discomfort. But anyway, that's what it is. Great. So let me start right away. So why are we doing this? So why are we studying systematically super conformal field theories, where kind of the ultimate dream of not just high energy physicists, but probably many more people, is to try to explore fully the space of quantum field theories. And many people in this, in order to explore this vast space, one strategy would be to try to study conformal field theories, what I call CFTs, which are much more constrained and much simpler to classify, and then see the rest and probe the rest of the QFT space by just studying RG flows among those theories. So already, this picture, it's a great picture and it's complicated, but CFTs by themselves already are very hard. I mean, the Bootstrap has done an amazing job in kind of systematically analyzing the space of CFTs, but it's actually a very tough thing to do. So, what do you do as a physicist once the problem at hand is too hard? Well, you add extra symmetry, and one obvious thing to do is to add supersymmetry. So that's what I call that's what they're called super conformal field theories. And in that setup, I think things are much more constrained, especially if you add enough supersymmetry. And I'll be precise on what that means. So what I will try to argue is that if you have enough supersymmetry in 4 dimensions, and I will justify why we restrict to 4 dimensions, momentarily, you can ask the question: can you develop a program to bottom-up classify what is allowed? Bottom-up meaning making really very limited number of assumptions, but of course you're making some, but trying to limit the number of assumptions as much as possible and try to aim at a general answer. Now, as we will see, once you're doing this exercise, and once you develop tools that are not based on perturbation theory and the usual Lagrangian setup, you discover that the space of quantum field theories that you're studying, it's overwhelmingly non-Lagrangian. So you have to really develop, in order to be successful in this bottom-up approach, you really have to develop something that goes beyond the usual kind of quantum field theoretic methods that you learn at the quantum field theory classes. And I would argue that the geometry of it's the answer. So those SCFTs come with a geometric gadget, which is the modular space of vacua, which I'll describe more in detail and briefly. And that's really something that allows you to give answers bottom up with high generality. And so, in my opinion, this is something that again, it's something that I've noticed, especially by trying to study systematically and enable 2 SCFTs and trying to kind of orient in the landscape. It's really remarkable how much of our current understanding of SCFTs is really tight with a string theory picture, which is amazing because string theory has given us so many results. But it's not clear to me whether there are many tools out there to really probe whether the string theoretic techniques can give us a complete picture. And so I think this bottom-up approach, which does not rely on string theory, really provides an opportunity to probe that completeness, which I think many of us somewhat believe that, at least with high enough supersymmetry and conformal invariance, you should be able to engineer and to generate those theories, to engineer those theories in string theory. So that's the kind of the motivation. And why 4D? Because we know, we have this picture that as you go down in dimensions, the complexity of the quantum field theoretic space increases, right? So you would like to try to classify at the highest possible dimensions. So it's a well-known results that superconformal field theories can only exist up to 6 dimensions, and we are really interested only in quantum field in superconformal field theories with at least 8 supercharges. So in that setup, the 6-dimensional theories that we're interested in are the so-called 1,0 theory. The 5D theory that we're interested in are n=1, and the 4D analog of 8 supercharges superconformal field theories are n=2. So those theories have a known R symmetry. That is SU2 in the first case, SU2 in the second case, and SU2 cross U1 in the third case. And what I'd argue is that while all of these theories are believed to have those moduli space of vacuum, these geometries attached to them. So in the case of, there are 2 main actors in the moduli space of vacuum. One is the Higgs branch, the other one is the Coulomb tensor branch. And while the Higgs branch is basically the same, has the same geometric structures across dimension, since the SU2R symmetry is spontaneously broken on the Higgs branch and gives a Higgs branch a hyperkähler structure. There's a unique feature of 4 dimensions that the Coulomb branch is far more constrained than it is in higher dimensions. And in particular, there's a U1 R symmetry that acts, and on the Coulomb branch is spontaneously broken on it. And so you can really rely on the power of complex geometry to constrain the Coulomb branch. So I would argue that really this extra constraining feature is which is probably well known to experts, but that's still something that singles out 4 dimensions. So the goal of this talk then is to try to leverage this extra constraining pictures from the bottom up. And basically the questions that we want to answer is, we want to try to classify all the space of moduli, all the possible moduli space of vacuum, which are compatible with being interpreted as coming from a 4D n=2 SCFT, and try to leverage that knowledge to really map the space of 4D SCFTs. Okay, questions about the motivation. Okay, great. So that's my plan. I would like to start with giving a very brief recollection for those that are not expert about what are the structure of n=2 moduli space of vacuum. Then I wanted to give a perspective on, tell you what the situation in rank 1 is, and it's a success story, though there's still some open questions which I would like to outline and call the attentions to it. And then I will move to the next possible geometry, which is what I call rank 2. I will give you a brief summary of what the state of the art of rank 2 is, and then close with providing a really strategy for classifying rank 2 geometries and possibly higher rank, and give you few recent concrete results that are really kind of remarkable on the genetic structure of for example the BPS spectrum of n=2 SCFTs. Great. So what is the notion of moduli space of vacuum? It's well known probably to most of the people on this call that supersymmetric field theories generically allow for a continuous set of ground states. So this is depicted in this beautiful picture here. In case of n=2 SCFTs, you have kind of different subvariety, different subspaces of this large set of continuous ground states. The 3 main actors are called the Coulomb branch, the Higgs branch, and the Mix branch. Those are highly complicated spaces which have high complex dimensions, and they also intersect among each other. So it's a kind of, I'm trying to understand these in details, it's quite complicated. So I'll be focusing on particularly the Coulomb branch. Let me give you, just for the few of you that who are not familiar with N=2 supersymmetry, what that is, at least in the Lagrangian setup. I'm not really using, I told you from the beginning, I'm not really using the Lagrangian intuition, but that just gives you the quickest way to get into what those vacua that I'm talking about are. So the N=2 free fields are, and the main actors of N=2 Lagrangian theories are the vector multiplet, the N=2 vector multiplet, and the N=2 hypermultiplet. The N=2 vector multiplet, it's decomposable in N=1 language into a chiral N=1 multiplet and a vector N=1 multiplet. So the interesting thing is that in general, these multiplets have a scalar which can acquire VEB. So I call the Coulomb branch, what is called the Coulomb branch is basically, in Lagrangian theories, is reduced to the space of vacua of the scalar in the vector multiplet. In the case, the hypermultiplet also contains scalars because it's written in terms of N=1 chiral fields. And the vacua of the scalars of the hypermultiplet is what is called the Higgs branch. So what are the, in order to just give a very simple example, if you have SU2 gauge theory, then the vector of the scalar of the vector multiplet transforms in a 2x2 Hermitian traceless matrix, and so the allowed space of vacua is what in the slide, which is just parametrizable by a single complex value. And there are two subtleties here that are not really subtleties, that phi is not a gauge invariant, so the real parameterization, the real parameter of your Coulomb branch is the square of phi, is u, what I call u. And in a generic point of the Coulomb branch, if phi is non-zero, you can see that SU2 is broken to u1. So in this case, the Coulomb branch is just a one complex dimensional space. And notice that the rank of SU2 of this gauge group is just one. So in general, you have, the dimensions, the complex dimension of the Coulomb branch is just given by the rank of a theory. Okay, so that's what is defined the rank of a theory. And we need the definition of the rank of a theory that does not rely on a gauge group, since we are going to be talking mostly about non-Lagrangian field theory, for which the gauge group just doesn't exist. So as I mentioned, the same structure that we see here in Lagrangian theories applies for non-Lagrangian theories. And so in generic point of the Coulomb branch, the effective field theory is going to be just very simple, just a bunch of U1s to the power R, where R is precisely the rank of the theory, which remembers is the complex dimensionality of the Coulomb branch. Since the theory is so simple, you can just parameterize it schematically by the Lagrangians, and you see that the tau ij, which are the holomorphic gauge coupling that parameterize the coupling between the various U1s, define a Kähler metric on the space. One of the major observation, which really that shows the intricate geometry of this space, is that this Lagrangian description is not unique. As you move around on the Coulomb branch, you're forced to move to a different electromagnetic duality basis, and to describe the full moduli space of vacua. Therefore, the fact that you don't have a unique Lagrangian, even though in a generic kind of open patch, it's very simple. It's very, very simple. It's just a bunch of U1s, gives you a lot of structures to play around, and in particular introduces this notion of monodromies. That means you turn, the fact that you're going around and you need to go to a different basis allows you to really associate extra structures to the space. So let me just summarize it in this schematic, in this kind of pictorial way. That's what we are dealing with. You have an R complex dimensional space, and here at the origin of the space, in most of the talk, I'm using all the real dimensions are in fact complex dimension. You have that your Coulomb branch has at the origin, you have your superconformal field theory, and out of the Coulomb branch you have lines where singularities arise. Why do you need singularities? Because precisely the fact that you have monodromies implies the fact that the metric going in has to be singular somewhere on the Coulomb branch. So that's the picture here. So you have those singularities because it's by going around singularities that your Lagrangian has to change, and it has to pick up an electromagnetic duality transformation, which is this particular group, which is SP2RZ, where Z is the integers, and the fact that Z, as the fact that the monodromy is in the integers, gives you an extreme constraining power. To give you a sense of how constraining this picture is, let's just give you one example. So I'm going to think generically that those UIs and UIs will represent the globally defined coordinates on this space, on this R complex dimensional space. So I go from 1 to R. Those are interpretable, as I said, as vectors of some operators. I described to you the fact that these have to be, in Lagrangian theories, those are vectors of the scalar component of vector superfields. But of course, in non-Lagrangian field theory, the thing is it's much more general, and you can characterize what is the type of operators that you need to consider the vev of, but that's irrelevant for the moment. You just consider UI as a set of vebs of operators. And of course, since your operator will have some non-trivial scaling dimensions in general, that carries over to UI. So you can ask, for instance, is there any constraints on the scaling dimensions of operators? I mean, those are the type of questions that you really try to answer generically, even with the bootstrap. Can I constrain generically by making no assumptions? What are the scaling dimensions of or some properties that is allowed generically on the space of CFTs? And in general, those questions are very hard to answer. In the case of Coulomb branches, instead, you can come up with a closed formula which constrains all the allowed scaling dimensions in general. And it only depends on the rank. It only depends on the number of Coulomb branch operators that you have, the Coulomb branch coordinates that you have. And you can see this is a closed formula, which was found by myself and Philip and Matteo Caorsi and Cicotti around the same time. And it just gives you the fact that all scaling dimensions of Coulomb branch operators of n equal to SCFTs have to be rationals and have to lie within a finite set for any rank. This will be used later to actually try to assess the completeness of our current understanding of rank 2 n equal to SCFTs field theories. Okay, any questions about that?
Yeah, are you talking here about all operators or only some kind of chiral operators?
Great, right. So these are Coulomb branch operators. Those are chiral operators, which are SU2, they are singlet of SU2R, and they have a special that's the special property that the U1R charge determines their scaling dimensions. I mean, the constant of proportionality depends on how you normalize the U1R charge. But those are particular chiral operators, bottom components of superconformal multiplet of n equal to SCFTs. But it's still non-trivial. Still from the bootstrap, for instance, perspective, it's hard to even see that they are rational. So it's still a non-trivial answer result. Does that answer your question, Adi?
I think so. It looks kind of intuitively clear, right? Because once you have one of them, you can just multiply and get the numerator to be an integer in the dimensions. And also, you know that a certain power of it will become trivial. So that's why I'm surprised it's so. It's not obvious.
What do you mean by it's not? I'm not clear. What do you mean by those are not important? So what do you mean by?
Well, it's generated by it has R generators, and if we stop multiplying them, the dimensions are going to add because they're chiral.
Right. So this constraints it's only for the generator, right? Those are constraints only of the generator, right? And so it's not obvious that at a given dimension.
The point is that with the generators, you generate everything. And there's no short distance singularity because they're chiral.
Right. Right. But what I'm claiming is that if you have only a single generator, for instance, that operators can have at most scalar dimension 6. If you have 2 generators, those 2 operators can have at most scalar dimension 12.
I see.
And that's not obvious to me that that's,
Okay.
you know,
No, the specific formula, I think, is not obvious, but the fact that there exists such a formula, I think is intuitively clear. But please go on.
great.
I mean, why is it intuitively clear that the R charges should all be integer multiples of some common rational number? I mean, what's true is that the Coulomb branch is some polynomial ring with n generators, but beyond that, but why should the generators have particular R charges?
Yeah, Jack, I share with you your. I mean, again, probably not. You know, of course, this is intricately connected with the fact that the monodromies are part of SP2RZ, and there's, but it's not. It's a little bit more involved of this. It doesn't seem obvious to me. Yeah, but I agree. Okay, great. Cool. Any more questions? Okay, great. So let me just quickly go through a success story, which is what this program provided in rank 1. So this is the results now from a few years ago. So we provided, you know, with Matteo Tito, Yan Chaolu, and Philip Argyris, we were able to run this systematic bottom-up analysis for a complex for Coulomb branch of one complex dimension, and we provided a full list of what are the allowed theories, and I mean, this is the list. The details are not important, but here is the flavor symmetry. For instance, here you can see that those are the scaling dimensions of the Coulomb branch operator, and you can see that basically they repeat, you know, the same numbers, and this is because this, you know, in rank 1, if you run the previous formula, the set of allowed scaling dimensions is incredibly constrained. It's just 7 of them, which are all realized, by the way, and so the interesting thing, just to kind of argue that this is a kind of a fruitful endeavor, is the fact that, for instance, only this 7 theories here had a known F theory construction at that time, and some of the theories actually were not known at all. Like, in fact, at first we were surprised that we thought that our assumptions were too weak because we got too many theories, but then, you know, there was a lot of work. And we were able to, you know, people were able to fill out the table and develop new F theory constructions, this n equal 2 S folds, which gave a multiple infinite series of new theories, including rank 2 and of course higher. And then you know, some people in the audience here have understood how to obtain all the theories from 60. Okay, so right now we are in the situation in which basically most of the theories in rank 1 have a known realization in string theory, and all of them can be, nearly all of them can be obtained in higher dimensions. But there's one mysterious theory that remains, and I'll say this theory is implied by basically RG flows from our perspective. I mean, I won't have much time to develop this thought more, but one of the huge advantages of this bottom-up approach is that you really can follow RG flows quite easily. And so the RG flows of the existing theories that were also realized in F theory shows that there is an extra theory here that must exist. To my knowledge, there is no known realizations of this theory outside of this kind of argument from the Coulomb branch. With Leonardo, Chris, Wolfgang, and Carlo, and I guess Madalena also, Lemos was instrumental in this. We think we have identified the VOA of this theory, but we still have to think a little bit more. And let me tell you a few interesting things about this theory. It has no Higgs branch, has no flavor symmetry. It's the only rank 1 theory with this curious property that the A central charge is larger than a C central charge. There's nothing that prevents that to happen, but it's a curious property, and the people here in the audience that are familiar with this kind of asymptotic behavior of the superconformal index of these theories know that this is kind of a tricky, it's a tricky kind of example to study. And the reason why this is not known, there's no known F theory realization, despite the fact that the theory that flew into this are realized in that theory is the fact that the mass deformation that we see on the Coulomb branch that takes you to this new theory is actually non-geometric. So you can't see it from the known currently theorized. So I think this is already interesting that even in the simplest case, we still don't have a fully complete picture. Questions?
Yeah, sorry, one naive question about this list of theories. Could I ask about the geometry that you get for the Coulomb branch in R3 cross S1 as a hyperkähler manifold fibered over the 4D Coulomb branch? In particular, I knew 7 examples of these hyperkähler fourfolds. Are you telling me that I have new geometries by these other examples?
Okay, so all these geometries are, they have basically, so those are not in equivalent Coulomb branches, okay? So that, I mean, this is a little subtle. In the scaling limit, when you turn on the masses to 0, basically they all have the same Coulomb branch geometries. I mean, it depends on the geometry of the Coulomb branch only depends on the scaling dimensions of delta U. So I don't think you get anything new from compactifying to 3D. What all the subtleties of obtaining this list is really in the nitty-gritty details of how to implement mass deformations on a geometric picture. So you don't have to think about each one of those being kind of a scale invariant rank 1 geometries that is different. Does that answer your question? Okay, great.
Mario, can I ask? So
Yes.
You are sure that this theory exists because you know a theory which should flow to it and you know the deformation.
Yeah, so you basically, sorry, Sean.
So that's the statement. I want to understand why you think it exists.
Yeah.
Okay.
So the point is that if the RG flows is just really implementing kind of splitting the singularities, right? And so the existence. So we believe that if there is a set of RG flows that trajectories, theories that are connected by RG flows, if you realize any of the theories, and especially if you realize something that is kind of mother or father that is above, then the rest is implied by necessity.
Thank you.
I don't see anywhere around, frankly, because basically, I mean, if this doesn't exist, then the other 2 theories above it don't make any sense from the Coulomb branch perspective.
Okay.
Great. Any more questions? Okay. So
does this theory have a counterpart, or maybe I should say a precursor, in 5 dimensions?
Sorry?
Does this theory have a precursor in 5 dimensions?
That's a fantastic question.
There are theories at the bottom of the chain in 5 dimensions which have somewhat similar properties: no Higgs branch, no flavor symmetry, etc.
Right. So the point is that so again, that's a great question, which I meant to try to think more deeply, but then I got distracted. That was a long time ago. But so I don't have an answer. The only thing is that the Coulomb branch scaling dimensions of this guy, it's 3, right? So this is basically once you turn this as a 4-star Coulomb branch singularity. So this would be kind of more. As a scaling dimensions, Coulomb branch is the same as the E6 rank 1. So it's kind of a little tricky to think that, once you go down instead in the list of rank 1 5D theories, the kind of what you obtain for the Coulomb branches changes. So I think it's unlikely that it's going to be one of the bottom one of the EN kind of series, but it's unlikely. I don't have anything more to say. That's a great question, though, and I'm sure that they should be thought about. More questions? Okay, so then given that the simplest possible scenario, the rank 1 scenario, which I think I don't want to speak for my collaborators, but certainly I didn't even think that it would give us so many new lessons because it's such a simple thing. We really thought that we knew everything about it. Given that was so fruitful, it's really important to continue that. And it's not just because we want to, there's some times in which you learn the techniques and just like, running with this. But, again, there's many things that incredibly simplify in rank 1. So rank one is really, the properties that we see in rank one really cannot be used to conjecture and to extrapolate at higher rank. So I think it's really important that we move to rank two and try to study that. So before doing that, I really try to understand the state of the art. I mean, it's a vaster space, and so I try to do that, and I mapped out in a recent paper all the known rank two theories. As you can see, I mean, this picture is just pretty, but besides that, you don't really need to learn anything here. It's just impactful that there are many more theories. Maybe a remark that are kind of obvious for the experts, but for the ones that are not experts, it's less obvious. Here, for instance, the shading means that the yellow and the purple ones are Lagrangian theories. The purple ones are n equal 4, and the yellow are n equal 2 Lagrangian theories. The green ones are n equal 3. And then you can see that once you have tools that move you out of the kind of comfortable Lagrangian regime, you see that the Lagrangian theories are sparse. But that's something that we, all experts know well, but I just that kind of the confirmation of that. So I've done this, and these are also organized in RG flows. This is something that Gabi and I worked out. Gabi more than me, thanks to the 5D picture. So, but will be coming out soon. So all the theories in this slide, they come from higher dimensions. But again, this is just mapping out what we already know. Okay, so one thing that I want to assess first, before I provide to you kind of an outline of a possible way to replicate the bottom-up approach in rank 1 for rank 2, I just want to try to look at the map of what is already known and try to assess whether or not there are hints that this picture is complete, or do we need to really spend time and try to understand better what's going on. And it's kind of a rhetorical question. The answer is I strongly believe it's not complete, and I'm coming to argue that and convince you guys that that's the case. So let me start from the fact that there's already in rank 2 a Lagrangian theories, which has no, to my knowledge, has no known string theory construction. This is a kind of a weird Lagrangian theories, you might argue, but it's nevertheless is completely legitimate. And that's an SP4 by of course, must be obvious that, but I used the conventions in which SP4 is rank 2 gauge curve. SP4 with a half fiber multiplied in the 16 that was first noticed by Balaccia and Yuji back in 2013. And again, has no Higgs branch. This kind of is really resemblant to the theory that we missing, the mysterious theories in rank 1. And again, has the unusual property that A is bigger than C. Haven't really, I mean, maybe that's our laziness. Haven't checked whether or not this is the only rank 2 theories with this property, but I wouldn't be surprised that it's, again, the only rank 2 theories with this particular feature. So these are already a Lagrangian theories that has no string theory construction, which I think it's something interesting. And then another interesting window into the completeness of our current understanding is provided by n equal 3 SCFTs. Why so? Because I mean, n equal 3 theories are nearly maximally supersymmetric. So they have a lot of the constraining picture that constraining features that n equal 4 theories have. They're very different in some senses. I mean, in many senses. In fact, they're necessarily non-Lagrangian and isolated. The fact that they're necessarily non-Lagrangian is what I think took so long for people to learn about n equal 3 theories, simply because if you write an n equal 3 Lagrangian, I mean, a Lagrangian that has n equal 3 supersymmetry, then necessarily that enhances to n equal 4. So people for many years believed that n equal 3 was just impossible, but that was learned that not to be the case. And again, the modular space of vacuum of n equal 3 theories is basically as constrained as n equal 4. You just lack the Lagrangian description, but nearly from the bottom-up perspective is nearly the same thing. So in fact, you can argue that these modular spaces of vacuum of n equal 3 theories can be written as orbifolds. Again, I'm changing the terminology from modular space from Coulomb branches to modular space of vacuum. And again, this is for the expert is obvious, but there is no really intrinsic definition of Coulomb and Higgs branch for n equal 3 or n equal 4 theories. So really what is naturally defined is the full modular space. You discuss the full modular space at once. Great. So basically, the fact that you can write them as orbifolds implies that you can map the question of classifying those geometries and those theories into questions of group theory, because you just have to classify these finite groups that act on the C to the 3R. R is the rank once again. So you did the exercise, and there's a bunch of us that have done the exercise of what are the possible groups that give you a consistent low energy n equal 3 effective description, and you find out that, I mean, this is a technical thing I'm writing here for the aficionados, but it's not important. It's a principally polarized crystallographic complex reflection group. That's what those groups are, and these are completely classified mathematically, and you can ask whether rank 2 all the complex reflection groups that are allowed have some n equal 3 theories that is realized in some known construction. And the answer is quickly no. I mean, I'm writing here just the more famous groups. There are actually possibly even more there. There's some subtleties there, but it's not important. But you can see that only these 2 complex reflection groups have a known string theoretic realization, the corresponding n equal 3 theories. There are others that don't. So again, this is something strange. It seems really to hint at the fact that simply we haven't been creative enough to come up with other constructions. These are just, I'm being conservative in pushing the boundaries of what we know is consistent and inconsistent, because actually there is no, to my knowledge, there is no bottom-up, kind of low energy argument to argue that these groups have to be complex reflections. In particular, there's no low energy argument to argue that the Coulomb branch Chiral ring has to be freely generated. So in fact, there are examples of non-freely generated Coulomb branch Chiral ring, which for the experts do not have a two-form symmetry. They don't come from a discrete gauge. They're just genuinely n equal 2 theories with non-freely generated Coulomb branch Chiral ring. They're n equal 3 supersymmetry. Those are even more exotic. And again, we have no idea on how to realize those. And actually, I think it's not even clear to me that it's necessary that n equal 3 theories have to be orbifolds. But again, you're probing, I'm probing here even more extreme corners of the possibility. But even be conservative, what I'm trying to argue, even trying to be conservative and just limiting to things that we really know they're perfectly consistent, there's many new theories which seems to be perfectly valid and have no string theory or a kind of known construction.
Mario?
Finally, and possibly more. Yeah.
Yes. I want to ask the same question about these theories as before. How do you know they exist if you don't have any construction?
No, we don't know they exist, right? So that's very, this new theories that I'm referring to, they're on different ground compared to the one that I mentioned before. The one that I mentioned before, I would argue that I know that it exists because there's energy flows that I can identify that flows into it. Those ones here, I'm just constructing a consistent modular space of vacuum. Okay. And you're right that does not imply, that does not prove that those theories exist, right? It's just a hint of the fact that there might be missing string theoretic construction. Okay. I agree completely. It's just a hint. That's in the realm of hints, not proof of anything.
Mario, a follow-up question to this. So in the case of the rank 1, your geometric construction from a bottom up, do you have a clear picture why all such examples can be realized in string theory?
Sorry?
Do you have a picture why?
I didn't, maybe I'm missing the end of the question. You said I have a clear picture of what?
So this is a question, a follow-up to Shlomo's question. So in the case of the rank 1, you can engineer these things from a bottom up, and then there is a counterpart construction from some stringy setup. Is it obvious, at least the analysis that you're doing, what it translates to from a string theory point of view? Or is it really completely different levers that don't necessarily overlap or have anything to do with each other?
No. I mean, well, of course, it has. It provides a lot of information, right? For example, in this known. Well, for instance, one thing is the Coulomb Branch geometries, the skin invariant Coulomb Branch geometry, right?
Yes.
Which again, it depends on the string theory, but for instance, in the F theory, it's very clear, right, from the kind of the 7 brane singularities and the kind of the deficit angle that you get by going around the 7 brane singularities in F theory, for instance. So there are things that map very clearly, and in particular, for instance, in the rank 2 n=3 theories that are realized in F theory, there's complex reflection groups really arise as some invariant groups of, you know, this theory is engineered as 2D3 branes probing a particular it's called S-fold, some generalization of an orientofold, and really the complex reflection groups is the kind of the symmetry group of the transformations that map the system into itself. So it's very geometric in that point of view. So there are certain things that clearly map very clearly in the string theoretic realizations, others that don't. And in fact, you know, I mentioned in rank 1, there's certain mass deformation, but I think that's known from many years ago, that not all mass deformations, you can see them from kind of motions of branes and stuff like that. They are not all geometric. So some mass deformations are very clear from a string theoretic perspective, some aren't. So in this case, we know the central charges, we know everything about this putative n=3 theories. So I think there's a lot of, at least there's a lot of initial data to play around with. Does that answer your question, Ibu?
Yeah, that got it. So from a string theory point of view, there's several different constructions. There's F theory, there's from M theory. Some of these constructions have obvious relations, some have obvious overlap, others don't. Some, even within the same sort of scheme, you can get two different things that initially are not the same, but then are the same by the time you flow. Should I expect from your analysis that maybe there is some structure within how we understand CFTs and string theory, which should be more uniform or not?
Oh, okay. Okay, great. That's a wonderful question. So what I said, you know, in the beginning is that I think I would be very reluctant to try to answer such a fundamental questions like you're asking based on my results, on our results on rank 1 theories. Simply because you might be deceived by the simplicity of the examples. That's obviously my take, especially having done quite a bit of kind of bottom-up analysis, at least on what is known in rank 2. So I think it's a little preliminary to try to answer that questions, because I mean, that's my conviction. Again, I might be proven wrong by history, but my conviction is that there's quite a bit of structures of n=2 SFTs, which we haven't really still understood. In my opinion, certainly, let's say if hypothetically we're able to fully understand the way we understand rank 1, rank 2 theories, I think already we could be in a place in which questions like you're asking that are really, you know, kind of fundamental can be addressed.
Okay, thanks. It's just that seems to be in the expectation in the rank 2 that there's at least a version of that is implicitly being assumed.
That what?
Well, the question that I was asking about having this other structure within the string theory itself. Yeah. Thank you.
Okay, good. So let's now point out one more thing that again I really hope that so I'm being upfront on my belief, but this is not, you know, please, if you have clear arguments that disprove some of the stuff that I'm saying, I would love to hear it so that I don't waste my time in trying to prove something that is already proven or something. So please feel free to you know, tell me very clearly if you disagree or if you think that some of the arguments are unfounded. I would love to hear that. Oh.
You were frozen, Mario. Are you still there? Okay, we lost the speaker. Oh, you're here.
People, can you hear me? Sorry.
Yes, we can hear you now.
Sorry, guys. I don't know what happened. It just collapsed and then re-entered. Anyway, sorry. Great. So Arcturus-Douglas theories are again a very set of n=2 SCFTs. it's not very clear that they really have kind of distinctive property, but certainly
Okay.
I'm sorry.
That's fine.
Still collapsing. So if it collapses another time, I will connect my phone. Okay. Sorry. Okay. So the property that really distinguishes them is the fact that they have fractional Coulomb branch scaling dimensions. So do we have a way to assess whether or not the Argyros-Douglas theories that we know, let's say rank 2, provides all of the Argyros-Douglas theories that are out there? Well, again, we don't have an answer. I don't have an answer that is definitive for that. But let me provide some argument. As I told you, you can run the formula that we discussed with Nadi and Jack about the Coulomb branch scaling dimensions of the general Coulomb branch Chiral ring for rank 2, and you get that those are this whatever number of rational entries is what is allowed a rank 2. So in the kind of if you go back to the huge set of tables of rank 2 theories that are currently known, you can just ask whether or not do all these allowed scaling dimensions are realized. Again, in rank 1, all the allowed scaling dimensions are realized. Again, this is clearly an assumption. There is nothing fundamental from the low energy perspective that tells you that all the allowed Coulomb branch scaling. So that, in my opinion, it's interesting, would call for at least some thoughts on whether.
Mario, you cut off for about 10 seconds.
Let me.
Do you mind just repeating what you just said? Yeah.
Yeah. So. Okay. So what I said is that that all the integer scaling dimensions are realized by known theories, and the fractional ones are instead, there is some interest that is not. Of course, there is nothing that proves that there is nothing that no low energy kind of constraints that imposes the fact that all the allowed Coulomb branch scaling dimensions have to be realized by actual theories. But it's at least interesting to put some thoughts in seeing whether or not we might be missing some of the theories which have this Coulomb branch scaling dimensions, which I highlight in the picture. And why is this even a meaningful thing to do? Is because if you actually go back and try to see whether or not there's been there might be Lagrangian theories of which we haven't really studied the Coulomb branch of. Again, to my knowledge, for instance, there are clear examples. In particular, I haven't seen a systematic study of the mass deformations of, for instance, G2 gauge theory with 4 sevens. This is one example. There's others, and yet, you believe that, for instance, this theory, the space of mass deformations, and in addition with turning on Coulomb branch parameters, it's a large one. It's 6-dimensional, and so you would expect that by playing around with those things, you should be able to engineer some fixed points, which would be some rank 2 Argyros-Douglas theory. Are those ones new Argyros-Douglas theories? Are the ones that already arise, for instance, on the Coulomb branch of SU3 with 6 flavors? Those are interesting questions. Again, I think they're called for a more systematic analysis because, as I said, there are interesting hints. Questions about it? Okay. So if there are no questions, and please, Ibu, tell me if my connection still doesn't work well, so that at least I try to go through everything and be clear. Let me conclude in the last 10 minutes by outlining how we go about it. How can we go about it, classifying from the bottom up, and try to also highlight some of the properties that we have proven, in fact. And those are interesting generic properties that, in my opinion, really kind of give you different lens on thinking about those theories. So remember, again, we go back to the kind of the more bottom-up approach. Right? We want to have something to say about classifying all possible rank 2 geometries. Right? So now really this picture should be taken somewhat seriously, where every single real dimension is in fact a complex dimension. So we want to try to come up with a way to study what are all possible such geometries. Again, remember that those geometries are comprised of a 2 complex dimensional base, of a 2 complex dimensional space, where at the origin it sits the SCFT, that is the rank 2 theories that we want to study of, and then there are complex dimension 1 lines, which represents the singularities that come out of the origin, and those are singularities, metric singularities, where the metric degenerates. Great. So we really, in order to do this bottom-up approach, some of the kind of more heuristic arguments that I've given so far are certainly not enough, and we really have to go and try to leverage the entire constraining power of Seiler-Witten theorem. And there's particular things, again, I'm simplifying and leaving technical details aside, but really in rank 2, the mathematical problem at hints is the fact that you want to try to study the full kind of Coulomb Branch geometric picture. It's tantamount to just taking this 2-dimensional base, which I told you, and imagining that at every point there is a fibration of a genus 2 curve. The singularities that I'm talking about arise when the genus 2 curve degenerates. I've tried to use my pictorial skills to show it. So you find some periods that go to 0. Of course, the expert might know that this is also oversimplified. There's also Seiler-Witten differentials that is defined. That is also another thing we have to construct. But let me just keep it at the geometric picture of understanding possible degenerations of genus 2 curves over these 2 complex dimensional bases. Great. So there are mathematical results on that probably many people in the audience are already familiar with. And in fact, the degenerations of the genus 2 curves was already completely classified in the 70s. Well, I guess in the 60s and the 70s by Ogg, D'Amico, and Ueno, which came up with the full list of what the possible degenerations of the genus 2 curve are, the allowed ones, over a disk. So let me tell you 2 things that really are important here. So number 1, if you actually run through the list of their generations, you find that the vast majority of the entries that they find are incompatible with scaling invariant special Kähler geometry. So that's actually good, because they find many entries and you actually left with a bunch of entries that are potentially physically possible. But the other news is not that good. The fact that the problem that they study is not really the problem that we need to study. The problem that they study is the degenerations of genus 2 curves over a disk, which is basically a 1 complex dimensional base. Whereas we are interested in the generations of genus 2 curves over 2 complex dimensional base. So what does the problem that has been solved by D'Amico and Ueno map to in our picture is basically, it would be tantamount to understand how the genus 2 curve degenerates moving into one of these complex dimension 1 singularities out in the Coulomb branch, not the one that you really want to understand, which is the SCFT at the origin. So one of the things that I think it's one of the most relevant kind of developments in the last, let's say, 6, 7 months, 8 months, has been the fact that we were able to completely reformulate the properties of the rank 2 theories at the origin in terms of the behavior away from it. Right, so we were able to completely determine everything, all those SCFT data at the origin in terms of the data on the complex dimension 1 singularities, on the rank 1 theories that leave the kind of non-trivial effective field theory living on this rank 1 of this complex dimension 1 stratum. So this is already kind of useful. This is incredibly useful for performing the classification, but it also gave us a lot of hints on how to think about higher rank theories in terms of this kind of simpler theories that leave on the singular strata. And in particular, if you go all the way out at infinity at the complex codimension 1 strata of this complicated space, which is the singular locus of this complex of the Coulomb branches, those theories are rank 1 theories. So you're basically reformulating the problem of understanding higher rank theories in terms of rank 1 theories. So let me tell you, for instance, one of such generic features that you can find, and it's actually, to me, quite surprising, is the fact that, you know, many people in this audience might know that it's incredibly hard to understand general properties of the BPS spectrum of n equal 2 SCFTs on the Coulomb branch. There's walls of marginal stability, things get, you know, BPS states decay, and it's very complicated. But one thing that, for instance, we can prove is that no matter what, you know, let's say you start with a theory of rank, to be concrete, rank 2, but this can be proven at any rank. You start with a theory with a certain flavor symmetry. For simplicity, let's say there's a single simple flavor factor. It can be even more complicated, and that you want a complicated, but let's stick with simple factors. What we can prove is that there's always going to be at least one singularities on the Coulomb branch where the massless states, the massless BPS states are, transforms under the full flavor symmetry. This is not at all obvious, at least to me, it wasn't obvious before. Let me elaborate on this. So the Coulomb branch parameters, this UI, the one that parameterize the space, are flavor singlet, right? So you turn them on to move out from your CFTs to your Coulomb branch, and clearly you're not breaking the flavor symmetry. That's obvious, right? But what is not obvious is that, so that implies that the BPS spectrum, the full BPS spectrum, transforms in non-trivial representations of this flavor symmetry. But the question is, could I concede the possibility that the states that transforms non-trivially are just the massive ones, and the massless ones instead are singlet and flavor singlet, or flavor singlet under one factor and not the others? And the answer is no. There has to be anywhere, somewhere on the Coulomb branch, where massless states arise which carry flavor charges under all flavor factors of your theory. Let me tell you why this is non-trivial. For example, let's say you have a rank 2 theory that has an exceptional flavor symmetry, okay? That could happen, and it does happen. Then these F conditions, the fact that you have to have somewhere on the Coulomb branch a massless BPS states, or in other words, a rank 1 theory, which carry that flavor symmetry, implies that any rank 2 theories which has an exceptional flavor symmetry, has to flow on the Coulomb branch to a rank 1 Minahan and Mashansky theory somewhere. That's just a fact. There's nothing, you cannot escape that. Again, this is actually very interesting, and you can see that you can learn a ton about the structures of the Coulomb branch and this moduli space of vacuum by doing that. I performed, some of the stuff that I've done in rank 2 is performing this kind of minutious analysis of the moduli space of vacuum by understanding all the flows anywhere for all rank 2 theories, and it's quite remarkable. So since I'm running out of time, I will not. The proof it's relatively straightforward. That's why I wanted to give it to you, but I want to have time. Just let me tell you that it's basically a generalizations of the technique by Shapiro and Tachikawa, and using the topological twist of n equal 2 theories. But so that it gives you a lot of power. And let me just conclude by providing this kind of heavy conclusion slides. And so with these new tools, right, with the fact that we now understand a lot about generic structures of modular space of vacuum of n equal 2 theories, I believe that a systematic classification which relies on leveraging the known results from the math literature, then using the fact that we now can connect what happens out in the Coulomb branch in the singular loci in the degenerations of one complex dimensional base to the origin. There is still a missing link, but we understand exactly how the physics works, provides at least 2 ways of completely classifying rank 2 theories, which I believe is possible. One is algebraic and one is geometric. And in general, as I hope I convinced you, there's a lot to learn from a careful bottom-up approach. And at least you can pose some questions, which I really hope that might kind of spark some interesting thoughts from you guys in trying to kind of realize one of these open questions that I've outlined. Thank you.
Okay, let's thank Mario one more time. And if there are any questions, please just unmute yourself and ask, and the Zoom will open for a while for questions.
Is it possible to summarize that statement of the reformulation? What does it mean that this extension over the codimension 2 singularity at the origin has been reformulated in terms of codimension 1 information?
Right. So the mathematical stuff, mathematically, this is the open questions. I mean, I can tell you.
No. That's the thing you said. You said you knew how to do that, right? You knew how to reformulate what was happening at the origin in terms of codimension 1 information.
Right. So I can tell you, it's okay. What I meant to say is that we reformulate the physical properties of the rank of what's happening at the origin to what's happening on the singularities. Right. The generations of the genus 2 curves on the complex, on the singular locus gives you information about the low energy effective theories, the rank 1 low energy effective theory that lives on that locus, right? So that's something that it's connected more or less one-to-one. And so what we've done, we have written formulas, explicit formulae, which connect all the physical properties of the theories living at the origin with the theories living on the struct. Okay, so now I have idea. I mean, these are formulae that are written, and that's one. There's no escape.
So sorry. So when you say the formulas, that must include like the family of Seiberg-Witten curves and the Seiberg-Witten differential, right? Like that is part of the physical properties.
No, so those are just formulas from central charges and so forth, right? So those are A, C, and basically what we have written all the physical properties of the theories at the origin, which are A, C, and the A and C is central charges and the level of the flavor symmetry, completely in terms of purely results that live out on the Coulomb branch. I have something to say about there are issues. So the things that we have to challenge now is to how to use that very valuable information to sharply reformulate the questions in terms of mathematics. There's I mean, it gets into technicality and there's clear ideas. One of the problems that we have, for example, is using the fact that, for instance, so one possibility is to use the fact, an algebraic approach, right? So we want to write then the Seiberg-Witten curve down explicitly, and we can write it in terms of hyperelliptic vibrations, right? And then one thing that is very clearly that can be derived from the formula, the formula constraint somewhat directly, is the discriminant of that hyperelliptic curve. The x discriminant on the right-hand side of the hyperelliptic curve. That's something that is actually almost directly constrained by our formula. The problem is that that discriminant, that quantity that's very well defined physically, is not clearly well defined mathematically. I mean, that discriminant is not a birational invariant. So that's the thing that really, it's kind of more or less, if I have to pinpoint what is the problem with matching fully these physical pictures with the mathematics, is the fact that it's not clear that that discriminant that is well defined for the physics has an analog well-defined status in the Namikawa and Ueno. And in particular, for instance, Namikawa and Ueno in their pictures, they write algebraic forms for those degeneration. But it's not clear that and you can compute the in terms of hyperelliptic curves, and you can compute the discriminant. It's not clear that there isn't another form, it's still in hyperelliptic form that has a different discriminant, right? And so that's, I don't know if that clarifies a little bit, but that's the obstacle. So we are still trying to map kind of the physics to the math.
I see. So unfortunately, I still didn't understand exactly what physical information you claim to be able to reformulate. It sounds like it in particular does not include the central charges, which would, as you say, be basically equivalent to the family of Seiberg-Witten curves and the Seiberg-Witten differential.
But the central charge here, I mean, usually the central charges here are used in two different terms. There's the central charges in terms of the central extension of the n=2 superalgebra, and that contains and then the A and C. What I meant is A and C.
Okay, I see. But just, okay, so the stuff that you can get, I just wanted to ask, do you expect that argument to be able to extend a higher rank? That information you expect to be able to recover from codimension 1 information?
That's already been done. So we've written a formula. That formula, it's valid for any rank. What is not, what is much harder is that in any rank, at higher rank, you don't have the analog of the study of Namikawa and Ueno, and you don't have the algebraic point of view. You no longer have this hyperelliptic form. You can still write things, some Coulomb branches in hyperelliptic forms, but it's not the most general. But yeah, the formula is already written for any rank.
Great, thank you.
Mario, I have a question.
Hey, Ashwin, hi there. Yeah.
Yeah, hi. Just to be clear, so each row in your tables, either for rank 1 or rank 2, they are conjecturally distinct superconformal field theories, and in many cases, they are actually known to exist. But in some cases, the underlying 4D Coulomb branch geometries may actually be the same between different rows. Is that correct, or did I misunderstand?
Yeah. So exactly. So the scaling variant, we make the distinction between the scaling variant and the master form Coulomb branch geometries. So
okay, so let's say I want to remember the mass deformed geometry. So let's say I look at the mass deformed Seiberg-Witten integrable system, the full thing together with the fibration data. Is that distinct between each row in your tables?
Yeah, that it is. Yeah, that is it.
So that okay, thanks.
Hi, Mario. Thanks for the nice talk. So I had a question about this one exotic rank 1 theory that you said has no Higgs branch, right? And you and some other collaborators possibly can realize the VOA. So I wanted to know if you have any idea about what geometric information on the moduli space the VOA might be describing in this case.
Yeah, so I don't think there's any geometric information. I mean, the VOA, as you said, the fact that it has no Higgs branch, it has to be one of the special VOA for which this object, which is called the associative variety of VOA, should give nothing. I don't think so. The thing that the VOA is sensitive to is for example, the central charge, and so the C central charge, and that's something that you can reconstruct from the VOA. Geometrically, I don't know.
The fact that there is no Higgs branch is also the case for this USP4 special theory at rank 2, right? So there you can compute everything because it's Lagrangian. So did you study the VOA algebra of that?
Yeah, so that's a good question. So we discussed it, but on the top of my head, I don't think at least I don't have any guess that comes to mind. But I agree with you. I mean, the SP4, you have everything, right? So you can compute the entire set of Chiral operators.
I have a question. Is it,
yes,
Mario, is it clear in principle that that everything can be obtained by studying hyperelliptic curve and not more general? Because in general, I just need to study some Seiberg-Witten geometry with some SP4Z bundle, and it could be the periods of a more general abelian variety. Right? At higher ranks,
right.
certainly
So
we know
great. So, and that's precisely what singles rank 2. That principal abelian variety at rank 2, they are one-to-one correspondence with Jacobian torus of genus 2 curves.
Okay.
And that's and genus 2. So at rank 3, all abelian varieties are Jacobian torus of genus 3 curves. So you can still use either the abelian variety perspective or the kind of the Riemann surface perspective. It's no longer, but again, it's not true that genus 3 curves are all hyperelliptic. Hyperelliptic curves is just a subset of genus 3 curves.
Yeah.
So that's true. That's why I think rank. I mean, this really singles out also algebraically why rank 2 is it's an achievable target. So we're not making any assumption in studying hyperelliptic curves in rank 2.
Right. Thanks.
Okay, if there aren't any more questions, we can stop the recording. They couldn't be more free.